problem 155, chapter 6, we have this sphere, which we are releasing it with velocity of v0 on this incline without any initial angular velocity. Initial angular velocity is 0. And we have friction between the sphere and this incline, and we want to find how much it's going to slip. So of course, because there is no angular velocity and we are giving it some linear velocity at the beginning, it's going to slip, right? It's going to slip, but the friction is going to make this sphere rotate gradually, and angular velocity is going to increase and increase. And in one point, v of the center is going to be r times omega, which means after that point, we are not going to have the slip. And the question is how long it's going to take for this sphere to go to that point. What's going to be the velocity and angular velocity, velocity of the center, and velocity, angular velocity of this sphere in that moment. So to solve this problem, first we need to draw the free body diagram and see what kind of forces do we have here. Here we have gravitational force, mg. We have normal force. And of course, we are going to have friction force. And because we have a slip, the friction force is going to be mu k times n. So these are the forces that we have on this sphere. So this sphere is not moving in the y direction. The centroid of it is just moving along this slope, because of that, sum of the forces in the y direction is going to be equal to 0, and it means n is going to be equal to mg times cosine of theta. Because of that, the friction force is going to be mu k times mg cosine of theta. And sum of the forces in the x direction is equal to mass times acceleration in the x direction, or actually we can use this equation, and sum of the forces in the x direction is going to be mg sine of theta minus this friction force, which is a constant force. So the acceleration is going to remain constant, and from there you can find velocity, which is absolutely doable. But the other way to get the velocity, and from that constant acceleration we can find the velocity. But the other way is using linear momentum equation. We can say hg, or g2 minus g1 is equal to integral of sum of forces in the x direction over the time. That's another way to find the velocity after some time. So if I want to use that equation, I'm going to have g2 minus g1 is equal to integral of from 0 to any time. By 2 I mean time t, by 1 we mean time 0. Sum of the forces in the x direction dt. So g is m times v, and at the beginning velocity is v0. So it's going to be equal to integral from z to t. Sum of the forces we have mg sine of theta minus the friction force dt. So from here we are going to have velocity at any time like t is going to be equal to v0 plus this integral, and this is a constant number, and the integral of it is going to be this constant number times t. So I'm going to have, and we need to divide it to m. We are going to have g times sine of theta, and the friction force is mg times cosine of theta, which we divided by m. So it's going to be negative g times cosine of theta. times t. Actually, we have mu k as well in the friction. So this is going to be the velocity of a sphere at any moment, at any time. Let's call this equation 1. We can do the same thing, but instead of using linear momentum equation, we can use angular momentum equation to find omega. So based on angular momentum equation, hg2 is equal to hg1 plus integral from time 0 to time t of sum of the moments about g dt. And we know hg is ig times omega. Ig times omega at time t is going to be equal to ig times omega 0 at the beginning, which is equal to 0, plus integral of sum of the moments about g. We have three forces here, mg and n. They are passing through g. They are not going to make any moment. The only moment we have is going to be the moment of the friction force, which is going to be friction force times r. And the direction of the moment is going to be in clockwise, which I'm going to assume it is the positive direction here. So I'm going to have from 0 to t friction force times r. So it's going to be mu k mg r cosine of theta dt. Again, this is a constant number. Integral of it is going to be all of these times t. So omega of the sphere at any time like t is going to be 1 divided by ig times mu k mg r cosine of theta times t. And also for a sphere, ig is 2/5 of mr squared. You can find that from the tables at the back of your book. And from there, omega is going to be equal to, if I replace this with 2/5 of m times r squared, omega is going to be equal to 5 divided by 2, 5 divided by 2 r mu k g cosine of theta times t. So whatever I'm writing here is it's for the duration of the slip, because after starting to purely roll, the friction force is not going to be equal to this, right? This friction force is equal to mu k times n if we have a slip. So these two equations, which are a consequence of this friction force, they are valid only for the duration of the slip. So we know it's gonna stop to slipping if velocity of the center become r times omega. So we know this is the velocity and this is omega. So if you have this relationship between these two, then the sphere is going to stop slipping and it's going to have pure rolling. So v0 plus g times sine of theta minus mu k cosine of theta times t should be equal to r times omega, so 5 divided by 2 mu k g cosine of theta times t. Now from here we can find time, at what time it's going to start to purely roll. So t is going to be equal to, if you simplify this equation, t turns out to be 2 initial velocity divided by g times 7 mu k cosine of theta minus 2 sine of theta. And to find the velocity in that moment, we only use this equation. Actually, after finding t, we can put it here to find omega. Then after finding omega, we can find the velocity as well. Those are simple things that we can do. So omega is going to be equal to 5 v naught mu k divided by r times 7 mu k minus 2 tangent of theta. And from here, velocity is going to be just r times this. This r is going to cancel out. So I'm not going to write that.